This is Geometry Semester 1. It's the unit on similarity. It's the 8th unit, and it's the second lesson called SAS, or Side Angle Side Similarity Postulate Practice. It's on CreatorMathcom under the Geometry tab. You might have to Google creatormath.weebly.com to find the website. The instructions are copy the following problems into your composition book on the correct pages according to the table of contents with the notes for those pages from CreatorMathcom. So we're going to do these practice problems, but before we do, I usually try to show you where the notes are and even briefly review them a little bit with you. So let's see if I can do that. Oh, here we go. There we go. So here's the website, creatormath.weebly.com, W-E-E-B-L-Y, right? Type that in, you should be able to Google this and get to this home page. Here's what it looks like here. If that's where you are. Any questions on the composition book, please just scroll down. If you scroll down to where it says composition book, right there, now you're going to know everything you need to do for the composition book. Watch all these videos, follow these deadlines, and follow all these directions on what to put where. If you do that, you should have a 90 to 100% on your comp book. And those notes are what help you to do these problems. So now I'm going to go to the Geometry tab. All of the notes, the video lessons, the problem sets, and the vocabulary is all under the tab of the class you're in this case Geometry. So this Vocabulary Geometry Practice Study PDF, every single vocabulary word we use for the entire school year in geometry specifically is on this PDF, and it is searchable. So if you don't know how to search a PDF, first download this to your device. Then go and Google how do I search a PDF for the device you're using. It's slightly different depending on the device. Now I'm going to scroll to the semester we're in. That's important. So for this video I'm making right now, this is semester 1. Here's the table of contents, and this should have been written a long time ago by you onto pages 2 through 6 of your composition book. If you haven't done that yet, please stop what you're doing now and write it in. Why? Because every one of these lines tells you what page everything goes on. And if you don't have this set up, you don't know where to put these notes, then the composition book is going to be a mess. But if you know where these go, then I can grade it quickly, and you can keep up, you can figure out what you're missing, etc. So let's go down to similarity here. Here it is. So this is the unit on similarity. It's got 5 lessons. We're on lesson number 2, which is SAS Similarity Postulate. Here are the page numbers that these notes go on in your composition book. Please don't use this video for the page numbers, but go back and find this original table of contents. By the time you view this video, probably these page numbers will be different. Here are the notes. These are the notes that go on those pages. The problems in this video solution will be right here when it's done. Let's click Notes. Oftentimes it takes a couple loads to get this image to load. It'll either be a picture of my notes in this case or a picture of the board. It just depends what I've got available. So these notes go on those pages in your comp book, but it's going to explain to you things like SAS is Side Angle Side Similarity Postulate. So what is similarity in geometry? It means proportional. I always try to pull out one of my models. Here's a model helicopter, right? This is a 1/48 scale model of a Dolphin made by Aerospatial Helicopter, which means that if you took the real helicopter and divided every piece by 48 and then put it together, you'd have this model. So this model looks exactly like the real thing, only it's smaller. It is different from the real thing by a scale factor, and in this case, the scale factor is 1/48 scale. Right? So the likenesses, if you saw the real thing, you'd be like, wow, that looks real. It's even got some features like the real one, right? It's got retractable landing gear, and they made it just like the real one too. So that's what a scale model is. That is what similarity means in geometry. It means proportional. So we're going to deal with two shapes here, in this case triangles, and we're going to ask, are they proportional or not? We're going to follow these postulates to see if we can figure out if they are. So are these two triangles similar, which means are they proportional? That means the exact same shape, but different size based upon a scale factor. So in this case, we say yes because of SAS Similarity Postulate. What does that mean? If we compare this side here with its corresponding side here, and we went from 5 to 15, so we multiplied it by 3, Then we have an included angle between the two side lengths, and we go to this side 10 and compare it with its corresponding side. And by now I hope you know that corresponding means the same location on different shapes. So this side is the same location as this side, except on a different shape. And this one's turned upside down, so we kind of have to either rotate it or change its orientation in our mind. We flip it in this case to see that it is the same corresponding side. So 5 angle 10. 15 angle 30. The 5 was multiplied by 3 to get 15. The 10 was multiplied by 3 to get 30. So in this case, the scale factor is 3, because we multiplied everything by 3 to get that. Now, the angles stay the same in a triangle, because you can't just go and multiply the angles by 3, right? So you're going to have to think through that. And now we can set up a proportion. We can say 5 over 15, 10 over 30 is equal to this, and it's equal to 1/3, right? So if we're going from large to small, the scale factor is 1/3. If we're going from small to large, the scale factor is 3. So, and here would be an example, right? If you've got this scale, helicopter is 1/48th scale, it's smaller than the original, because you had to divide that larger size by the 48 to get down to the smaller size. If you were going from small to big, you would multiply it by 48 to get back up to the big size. Okay, so anyway, you're putting these notes into your composition book on the correct pages, and these are going to help you solve the problems we're about to do right now. Here's some vocabulary. Similar means proportional. Proportional means larger or smaller based on a scale factor. Proportional means one fraction made, a proportion is one fraction made equal to another. We'll see that in our problem set here. Here's the symbol for similar. Here's the symbol for congruent, and just a reminder that congruent means same shape, exact same size. So congruent, equal corresponding side lengths and angles of triangles. Those would be congruent triangles would fit this definition. And a scale factor, the consistent factor by which two similar triangles are related. So you would either enlarge a smaller shape to a bigger shape, or shrink a bigger shape to a smaller shape by a scale factor. And those, of course, are proportional or similar in geometry. So with that, let's go ahead and cruise through some of the questions. First question, what does congruent mean? Congruent in geometry means the exact same shape, the exact same size. And I would offer to you, instead of using equals, we used 3 equals 3, right, back in the old days, because it's one aspect of equality, 3 equals 3. But now all of a sudden we're dealing with angles, and we're dealing with side lengths. We don't want to know just that the angles are equal, but we also want to know that the side lengths are equal to come up with congruent. So instead of saying equals now we use congruent to show that two shapes are not only the same shape, but exactly the same size. That's the meaning of congruent. Now let's switch to proportional. What does proportional mean? It means larger or smaller by a scale factor, and we use the word similar in geometry. This word is problematic because in your regular language, when you say that two things are similar, it just means that they generally are kind of alike. But in geometry, it's a very specific meaning. It means proportional or a scale model. So what's the symbol for congruence? Here it is right here. It is an equal sign with a squiggly over it. What is the symbol for similarity? What is the symbol for similarity? It's right here. It is a squiggly like that. Look at the top left corner of your keyboard, and there's a similar squiggly up there that you can look at. So here's our first problem to look at. Are the following shapes similar? If so, why? Are they similar? If so, why? Drawings may not be to scale. So they can draw these in a way that can trick us, all right? And we can't just look at the shapes. We have to look at the data involved. So first things first, let's try to line these up. I'm going to rotate this one around this way. If I rotated this one around this way, it would look more like this. And if I rotated, the F would be way over here. The D would be here, and the E would be up here. Okay, so DEF, now it's DEF. We just rotated the thing. So now this one looks like this one in the same orientation. Orientation is its position in area here. Okay, 36 would come down here. That's the length of this side. 15 would rotate around to here. And the angle between them, called the included angle between the two sides, is equal to this one here. Notice that for 5, the 5 is going to 15. We multiplied it by 3. The 12 is going to 36. We multiplied it by 3. So these two are related by a constant value called a scale factor. And in this case, when we go to small to large, it's 3. If we were to go from large to small, it'd be 1/3. We'd have to shrink it. So the answer to this is yes. Triangle ABC is similar, there's the similar symbol, to triangle DEF because of side angle side SAS similarity postulate. So given two triangles where the sides are proportional by a consistent scale factor and the included angles equal, we get to say that those two shapes are similar or proportional. One of them is a scale model, the smaller one is a scale model of the larger one, right? And I think you could say it the other way too. Typically scale models are smaller, but they don't have to be, they could be larger. All right, let's see what we got here. It is given that the following two shapes are similar. Oh, nice. So they're telling us these are similar. What is the scale factor from triangle ABC to DEF? This is ABC, this is DEF. It's the same one we just did, you guys. So the work we did on the last one, we're going from 5 to 15, which is times 3. And we're going from 12 to 36, which is times 3. And a scale factor has to be consistent. So if it's for one and it's for the other, this is a scale factor of 3 because we're going this way. Okay, and I'm just assuming we're going this way because I'm going left to right. Oh, it tells us here. I'm not assuming. We're going from ABC to DEF, right? So it's times 3. If we were going back the other way, if they had said, what's the scale factor from DEF to ABC, now we'd have to say 1/3. Oh. It is given that the following shapes are similar. They are similar. What is the scale factor from? Look at this. Triangle DEF to triangle ABC. So now they are going in this direction. So these are the corresponding sides here because we flipped this one before. We saw that. So this is being divided by 1/3. 15 is going to 5. So now we're going this direction. How do I know? Because we're going DEF, this one, to ABC, this one. We're going from one to the other. We're going from large to small, so we need to shrink. That means multiply by a fraction, or really it means divide by 3. Right? So the scale factor here going in that direction is 1/3. Are the following shapes similar? If so, why? Drawings may not be to scale. So let's trace it through. Let's rotate this thing again. Let's put this hypotenuse down here, which is the longer side. I see it more like this and this. That would leave the 50 here, the 40 here, and the angle between it is double tick mark, which matches with this. So the 10 and the 50 are corresponding, same location on different shapes. The 8 and the 40 line up, and the angle between them, called the included angle, is equal to the included angle. That's good, check. So looks like we have side angle side, but when we go 10 to 50, what do we multiply by? We multiply by 5. When we go 8 to 40, what do we multiply by? Nice, we multiply by 5. That's good. We need to multiply by a consistent scale factor. If it changes for one of the two sides, then we do not have a proportional or similar shape. So this is yes, triangle ABC is similar or proportional to triangle DEF because of side angle side SAS similarity postulate. And we do need to say similarity here because remember there are congruency postulates too that sound exactly like SAS. So we need to be very careful to distinguish in this case similarity or proportional. It's given that these two shapes are similar, so these are similar. What's the scale factor? So we're going this one to this one. We already calculated this one is 5. We did it on the last one. The 10 is going to 50, and we rotated on the last one and redrew it. Just back up the tape and look at it. The 10 to 50 is times 5, 5x, right? Or times 5, or multiplied by 5, or 5-fold. The 8's going to 40, which is 5-fold. The scale factor on this one from ABC to DEF is 5. I think I know what they're going to ask us next. Now let's go in the reverse direction. Let's say we're going from this to this one. Same problem. So now we're going from 40 to 8. So now we're dividing by 5 or multiplying by 1/5. So the 50 is going to 10. So that's consistent. Scale factor is 1/5. Make sure you're matching up the title of this video, with the actual problem set so that you do not become confused. This is Geometry Semester 1. It's the unit called Similarity, number 8. And it's the second lesson called Side, Angle, Side, Similarity Postulate Practice. It's on CreatorMathcom under the Geometry tab. Hope that helps.